This is the second lecture of topic 30.1 arenes of topic 30 hydrocarbons. Now, in the last lecture's last slide, we saw all of the reactions of benzene that we need to know for A levels chemistry. In today's lecture, we'll go through in detail of all of these reactions of benzene. Okay, so these are all the reactions that you will study, and this slide was shown in the last lecture as well. You can see you need to know about electrophilic substitution and these four reactions which occur by the mechanism of electrophilic substitution. You need to know about oxidation of side chain, reduction of side chain, and hydrogenation. Now, we discussed the mechanism of electrophilic substitution in the last lecture, and we will come to these four types of reaction that occur by this mechanism later. But right now, I want us to start with the easiest reaction of benzene, hydrogenation. In hydrogenation, benzene reacts with hydrogen, 3 moles of hydrogen, 1 mole of benzene reacts with 3 moles of hydrogen to produce cyclohexane. You see all of the pi bonds have been broken, and now benzene is no longer benzene, it is cyclohexane, and all of the carbons are now saturated, which means that they're not forming a double bond. They are attached to other carbon atoms or other hydrogen atoms by sigma bonds. And this whole process occurs in the presence of platinum or nickel catalyst. This is the easiest reaction of benzene you will come across. Okay, now I want us to come to halogenation of benzene, for which we require a halogen, and halogen carry a catalyst of course, benzene. These are all the reactions of benzene. Now, what do we need the halogen carrier catalyst for? We need the halogen carrier catalyst to polarize this halogen to generate a strong electrophile. Now, if you remember the last lecture, we studied that we need a powerful electrophile to react with benzene because its delocalized ring of electrons is pretty stable. And so, it needs a very powerful electrophile. Now, in halogen, it has just two halogen atoms, and both of them just exert the same force on the bonded pair of electrons. So there's no polarity. So we need the halogen carrier catalyst to induce polarity in the halogen. And that's how. What happens is this AlCl3 causes this to polarize, and then we generate ions, AlCl4 minus and Cl4 plus ion. Now this acts as the electrophile. You can see the second step of this reaction. This is basically electrophilic substitution. This delocalized ring of electrons is attracted to this electrophile, and we show this by drawing a curly arrow from this delocalized ring of electron to the electrophile. And then we see that two electrons move from this delocalized ring of electron to chlorine in order to form a bond with chlorine. And you see a positive charge is left over here, and two electrons from the CH bond move to neutralize this positive charge, and our ring is reformed, and we also have chlorine attached to benzene. Now this is chlorobenzene, and we also form H plus ion, and then this H plus ion reacts with the AlCl4 minus we generated here, and we form HCl plus AlCl3. Now you can see that AlCl3 has been regenerated, and it has acted as a catalyst. Okay. Now you also need to know that if we have excess chlorine, we will get multiple substitution. Not just one hydrogen will be substituted by chlorine, but many others as well. Now what if we change the conditions from halogen plus halogen carrier catalyst to halogen plus UV light? A totally different reaction is going to occur. No electrophilic substitution will occur. Free radical substitution will occur instead. You can see that this chlorine molecule went through the initiation step of the free radical substitution you studied in AS chemistry, and you can see that the Cl substituted a hydrogen atom in the methyl group. Now, again, if you have excess chlorine, we will get multiple substitution. So instead of this becoming CH2Cl, this will become CHCl2 or CCl3. We'll get multiple substitutions if you have excess chlorine. Okay, up till now we have seen the reactions benzene plus halogen in the presence of a halogen carrier catalyst to form chlorobenzene plus hydrogen halide, and this is electrophilic substitution. And secondly, we have seen methyl benzene reacting with halogen in the presence of UV light to form this. Okay, now what if I react methyl benzene with halogen in the presence of halogen carrier catalyst. Well, now what will happen is that the halogen will substitute an hydrogen atom somewhere else in the benzene ring. Not this CH3, not substitute this whole methyl group. Okay. And it can attach here or here or here. You might have noticed that I only point out locations that are near the CH3 group or directly in front of it. And there's a good reason why the chlorine atom will only substitute a hydrogen atom at these specific positions. This one, or this one. We'll get to that later, but for now, it does not attach here or here at some other place. Okay. Okay, now nitration of benzene. You require concentrated nitric acid and concentrated sulfuric acid for that. You need these to generate your electrophile, and they will react together HNO3 plus H2SO4, and you will get H2NO3 plus HSO4 minus. We do not have our electrophile yet, and another reaction occurs. H2NO3 splits into NO2 plus H2O. Now this is our strong electrophile required for the electrophilic substitution. Again, the same process of electrophilic substitution occurs. This delocalized ring of electrons is attracted to this electrophile, and two electrons move to form a bond. A positive charge is left, and now two electrons from the CH bond move here to neutralize the positive charge, and our ring is reformed, and we have the hydrogen atom substituted by the NO2 group, and we also form the H positive ion, obviously. Okay, next happens is that this H plus reacts with this HSO4 minus to regenerate our catalyst, which is H2SO4. Consider sulfuric acid basically acts as a catalyst. Okay, anything that regenerates itself in the reaction and just helps the reaction to occur overall, is a catalyst. Okay, note a temperature below 55 degrees Celsius ensures a single NO2 substitution. If you use a higher temperature, you will get multiple substitutions. And here we have reacted methyl benzene with dilute HNO3. Now, methyl benzene is way more reactive than benzene. It does not require this catalyst. It is also fine with the nitric acid being diluted. And again, we get substitutions. And as we studied before, methyl benzene does not allow substitutions just anywhere. It only allows electrophilic substitution to occur near it here or directly in front of it, not at positions. If you count, if this is 1, this is 2, this is 3, 4, 5, 6, it does not allow substitution at carbon 3, 1, 2, 3, and carbon 5, 4, 5. This at this position, it does not allow electrophilic substitution here. And as I said before, we'll get to it later, but right now, just remember that the methyl group or other groups can influence the positions where electrophilic substitution occurs in the benzene ring. Okay, types of groups attached to the benzene ring. We're finally here. Now, there are two types of groups attached to the benzene ring. Let's first study electron donating groups. These groups have an electron donating nature, or you can say a positive inductive effect, and they increase the electron density in the ring at carbons 2, 4, and 6. Examples are NH2, OH, and CH3. Like a methyl group, it only allows substitution to occur at carbon 2 or 4 or 6. 4 is directly in front of it, and 2 and 6 are near it. It makes sense that the electron donating group like CH3 donates the most electron cloud to carbon atoms that are near it, like carbon 2 and carbon 6, and to the carbon atom that is directly in front of it, like carbon 4. Okay, now electron withdrawing groups. Now, electron withdrawing groups act in an opposite way to electron donating groups. These groups withdraw electron density from the benzene ring, especially from carbon 2, 4, and 6. This means the electrophile is more likely to attack at carbon 3 and carbon 5 because there's more electron cloud there. Since the electron cloud has been withdrawn from carbon 2, 4, and 6, it has been left, you can say, at carbon 3 and carbon 5. So that areas are now more attractive to the electrophile. Examples include groups like NH3, NO2, and COOH. Now you need to remember these examples of electron donating groups and electron withdrawing groups. And now NH2 and CH3 and OH, they are very, very powerful electron donating groups, especially OH and NH2. Okay. Now back to electrophilic substitution reactions of benzene. Benzene is a very useful substance, but due to its stable delocalized ring of electrons, it is difficult to react and modify into our desired products. A way to get around this problem is to make benzene go through Friedel-Crafts acylation reactions or Friedel-Crafts alkylation reactions, where we basically add an acyl group or an alkyl group to benzene. So let's study Friedel-Crafts acylation first. Okay, we need a acyl chloride and halogen carrier catalyst. The halogen carrier catalyst helps us to generate a strong electrophile, which is this. The AlCl3 helps us to generate a strong electrophile, which you can see here is RC double bond O. Okay, and we have a positive charge on this. Now, this is a very powerful electrophile that can react with the benzene. Now, we make this less stable phenyl ketone which is easier to react. Okay, this is made under reflux and dry ether solvent. The same electrophilic substitution process occurs. The only difference is that this H hydrogen atom is attracted to this negatively charged molecule, okay, and we form HCl and AlCl3. These two combine and this separates and we have regenerated our catalyst. So we're done. Now Friedel-Crafts alkylation, it is very similar to Friedel-Crafts acylation. Again, we require a halogen carrier catalyst and a chloride, but we need an alkyl chloride for this one. Again, AlCl3 polarizes this, and these electrons are attracted to AlCl3 and we form our electrophile and AlCl4 minus, and this R plus is a powerful electrophile that now undergoes electrophilic substitution. This ring of delocalized electrons is attracted to this one, and two electrons move from here to form a bond with this, and two electrons from CH bond move to neutralize this positive charge, and again this H plus that is going to form soon is attracted to this AlCl4 minus, a negatively charged molecule, and we form HCl, AlCl3, and this. Now, the second reaction after the generation of the electrophile occurs under reflux and a dry ether solvent. Now we make this alkyl benzene. This phenyl ketone is from the previous slide. Okay, this is a mistake. It is not a phenyl ketone. This molecule over here, it is an alkyl benzene. Okay, now we're done with most of the reactions of benzene, and only two are left, which are pretty easy. Not as easy as the hydrogenation, but very easy. Okay, oxidation of side chain methyl group and reduction of side chain nitro group. These are the only two reactions you need to know except for the electrophilic substitution reactions and the hydrogenation reaction. Okay, now what happens in oxidation is that this methyl benzene, okay, you see this methyl benzene, this undergoes oxidation, okay, and we form this COOH group instead of CH3, which is a carboxylic acid. And the conditions we require are alkaline KMnO4, dilute H2SO4, and heat. And as far as reduction is concerned, we have our nitrobenzene, and with concentrated HCl, tin, and heat, it is converted to phenylamine. Okay, that's all for today. Thank you.